All right, we're gonna get started, guys. So we have a special treat today. We wanted to give you a little introduction to part of our GTA team.
I'm Katie. Hi. Hi. Oh, so nice of you guys to say hi back. Oh my goodness. We thought it would be helpful to introduce ourselves before this first test, just to show you guys that we're not scary people. We're humans just like you. So please come visit us in office hours. And we thought that we might make ourselves more approachable if we shared something embarrassing that's happened to us recently, because we're all just trying to figure it out. My thing comes to you from this morning. It was rough. I made lunch for myself, which was super exciting, taking care of myself, and I spent like a full 10 minutes looking for the Tupperware to put it in, and I looked at it at least 20 times because I took it out at the beginning of the 10 minutes, and it was just sitting on the counter for me. I was walking all around the kitchen trying to find it, and it was just right there. So we're just people too. Also, I don't really believe that there are adults. Thank you for that. I did find it, which I'm very proud of. I actually don't think that any of us are adults. Some people are just better at pretending than other people, so don't take us too seriously. Come to our office hours and ask all of your questions because we want to see you. And that's my story.
I love it. Well, on that note, I think I try to be an adult. It doesn't really work out most of the time, but I am also part of this team. Come to office hours. I had to think really, really hard of what embarrassing story because I actively do not put them into memory. But I guess it's kind of embarrassing probably 3 times a week. I wake up really early, not by choice because I have to, and then I reach for the door handle and I miss it pretty frequently. So it's kind of did anyone see me? I'm in my room, but did anyone see me do that? Kind of like when you fall on ice. So yeah, that. Come to office hours. If you want to just come and say hi, maybe complain about chemistry. Sorry, I hate chemistry. You can do that, and then we can talk about physiology or just not at all, but come say hi. Definitely approachable people.
Thank you.
Yeah, thank you.
Yes, and I am constantly aggravated with the number of walls that just move sporadically and are in my way. So, we're just human. Is that okay? Okay. And also, hey, talk about embarrassing moment. I'm about to flash you. So yesterday, we talked about cell junctions, and we started with anchoring junctions. We talked about how hemidesmosomes can connect a cell to the basal lamina below it, and how desmosomes will connect a cell to a cell. Today, we're going to focus more on occluding and tight junctions. Those are ones that are going to hold cells tightly together so that things can't pass between them. And then we're going to talk about gap and communicating junctions, which allow for passage between 2 cells so that you can actually have small ions, small molecules passing from one cell to another. Then we're going to talk about a special type of epithelium. It's an exocrine gland, one of 2 types of glands we have in our body. And this is going to be made up of surface epithelium, duct epithelium, and secretory epithelium. So they're all epithelial cells. They're just in slightly different locations and have different transporters and receptors and stuff on them. We see these for salivary glands and sweat glands, as well as mammary glands. We are not going to talk about mammary glands here because mammary glands are under hormonal control, have to do with pregnancy and postnatal blah, blah, blah that's talked about in repro. So we're not really going to start on that yet. I will tell you though that mammary glands are just modified sweat glands. Okay, so it basically works by the same mechanism. So we'll just kind of give a general overview of how an exocrine gland works. And then we're going to talk about our second tissue type. That's going to finish up epithelium. And we're going to move into connective tissue. So unlike epithelium, which was really nice and organized in these layers with all these cell junctions between them, your connective tissue is going to be cells that are separated. And then they're going to secrete a matrix that it is embedded in. The connective tissues are going to differ by the type of extracellular matrix that is made. So one connective tissue might have more of one type of protein another connective tissue has another type of protein. It's based on its function. And we'll go through the different connective tissue types, and then there's some subtypes to this as well that you'll know. So we've got cartilage is our first connective tissue. Cartilage is going to be things like, well, we've got lots of things. Stuff in your ears, discs in your back, connective tissue. That's going to be things like ligaments and tendons that hold bones to either other bones or to muscles. Also, this is going to be dermis. So we'll talk about this with skin. That's what's going to be below your epidermis. Bone might seem surprising that it's actually connective tissue, separate cells, but it just secretes a big enough and heavy enough extracellular matrix that it makes it really hard, like cement. So we have very hard bone. This one to me is always the most surprising, blood. It's kind of weird to think of that as being connective tissue, but it comes from the same cell type, and the cells that the blood are made from are going to be embedded in this matrix. Once we get down to like erythrocytes, that's fluid, but the cell types they come from will be connective tissue. Right? Any questions from yesterday on the hemidesmosomes and desmosomes, the anchoring junctions? No? Okay. So then we'll talk about occluding or tight junctions. Oh. So this is two. This is an occluding or a tight junction. So if you have two epithelial cells, there's going to be a little bit of space between them. Nowhere near this much space. I just drew terribly. You'll have those anchoring junctions. They're going to hold them in place, but they're not necessarily going to pull them tight together. There will still be space between them with the anchoring junctions. With occluding junctions, we're going to have a transmembrane protein which could be an occludin. It's the easiest one to remember because it's just like the name of the junction. It's also claudins. And you might sometimes see jams. I'm sure that's an acronym, but I didn't think to look it up, so I couldn't tell you what that actually stands for. Did you have a question? Okay. These are the two I really want you to know. Occludins and claudins, those should be fairly easy to remember that they go with the occluding or tight junctions. If we were to mention jams, we'll tell you what it is. Okay, so if you have this transmembrane proteins on each cell, we're going to say that's an occludin. And here's another occludin. What happens is they want to connect in this extracellular space between the cells. And so they will pull this portion of the membrane closer together. And basically zipper it so that things cannot pass between them. I'll put that here. Prevents passage. Of course, this isn't a 2D, right? So I brought a prop. Spent a lot of time and energy on this. This is what I think of when I think of tight junctions. Okay, you've got these cells that are lined up next to each other, and they'll have anchoring junctions that hold them in place, but they're also going to have these zippers that are made from these tight junctions on the top and bottom. Okay. So if you were to take, this would be this cell here, or if we looked at two of these, this would be that cell and that's that cell. If we now turn it out so that you can see it, you actually have those proteins running the whole length of both sides of the membrane to zipper the whole thing. So it's going to just keep that entire cell zippered. So now you can imagine if you had these cells and you tried to push something through, you can't actually get them through. All right. So that's a tight junction. Any questions on that? You guys are so quiet today. It's not Friday. Yeah.
So does the Cloudins, do they do the same thing then if they just make it target?
So I gave you the example of an occludin here, and I said it could also be things like an occludin or a jam. Yes, it's going to do the same thing. They'll have slightly different structures because they're different proteins, but they'll have the same effect where they're going to pull these membranes together and then hold them. Okay. I want to point out too that these are just these transmembrane proteins. You could think of them like a snap on a shirt. You're going to have one piece on each side. You can snap them together and that's fine, but you can also pull these apart fairly easily. This does not have that protein plaque and the filaments to really cement that down. This is not meant to hold it. This just zippers it. Yeah.
If we have to cut urine with the desmosomes, why do we need these as well? Because the desmosomes hold the cell to cell, so what's the purpose of that?
So the anchoring junctions do not hold cell to cell. You're still going to have space. So you would have, if you had your anchoring junction in here, like a desmosome, you'd have a protein plaque, and you have these transmembrane proteins between it. But it doesn't actually pull those cells together. You could still pass things through here. But it will get stuck here. All right. Let's do communicating or gap junctions. This is going to be a hydrophilic intracellular channel. Intracellular meaning it goes from one cell to another. So now we have a means of being able to have this cytoplasmic continuity, meaning that we can move things that are in the cytoplasm of one cell into another cell directly through this. So we have our epithelium. We're going to have a transmembrane protein. Called a connexin. Because, hey, it connects the cells. So what this will look like is not this, but this is a cartoon representation of what it would look like. This is one connexon. Your other cell would also have a connexon, this transmembrane protein, and they will meet in the middle. Connect up, and now you have a pathway from one cell to the next. This is just a channel. It's not powered, so you still have to be able to use things like diffusion. So if you had in the cell a high concentration of sodium, but over here you have a fairly low concentration, well, now you have a gradient to diffuse. You're always going to diffuse from your high concentration to your low concentration. So this sodium wants to go where it's less crowded. And it can pass through that channel. And now it'll be over here. So ions could definitely go through here because it's hydrophilic. So anything charged has no problem. Cytoplasm itself has no problem. Small amino acids, maybe. Not when you start putting them together into proteins. This will not fit proteins. All right, so this is just where we're going to communicate with things primarily like ions. Now, we always give you the cell junctions on epithelium. We use the epithelium as an example. And we do that primarily because epithelium has all of them. So it makes for a really great example. But other cell types will have some of these junctions. typically not all of them, but some. And we're going to see these gap junctions again. These are going to be in cardiomyocytes, which means heart muscle cell. We have to pass a signal from one heart muscle cell to another in order to cause our heart to contract. And we pass those signals through these ions, through those channels. Okay, so we'll see this one again. Now this connexon, let's go a little deeper. This is going to be made of 6 connexins. So if this channel is actually running in the plane of the board now. If you were to turn it so that the channel was running out of the board and into the board, you could see that the channel itself is made up of 6 connexins. 3, 6, okay, good. So each one of those is a connexin. Put them all together, and it's a connexon. This is our monomer, that's our polymer. Questions on gap junctions? Any cell junctions? Okay. Then we can move to exocrine. So these exocrine glands, like I said, they're just specialized epithelium. And I also said that we have 2 types of glands in our system. Besides the exocrine glands, we're also going to have endocrine glands. Endocrine glands are important for hormones, releasing hormones into our blood. We won't talk about those for a while, even though we're going to talk about endocrine on Friday and Monday. We're not going to talk about the glands themselves until we get to digestive. But the exocrine glands, like the name suggests, exo, these are going to the outside world. So this is something the body secretes and then you release. We also can call these ducted cells or ducted glands because it has a duct it has to go through. So, here is our nice, organized, layered epithelial cells. Well, at least they were nice. I'm getting tired. There we go. To orient you, we know that epithelium always has to be on a basal lamina. Here's the basal lamina for these. Okay, so that's your basal lamina. That also tells you that that's the basilar surface of every one of those cells. The apical surface will face the lumen, or the outside world. So this is apical. This is the outside world. Oh, I screwed myself up. All right, I'm going to make this a little bit shorter so I have more room. We have the 3 different cell types that we mentioned. They're all epithelium, but we're going to have, this is called surface. Surface epithelium means that it's in line with the surface. These cells on the side that are lining this duct are your duct epithelium. And then the cells that are at the bottom of this duct, these are secretory epithelium. So that's where you start. You're going to take something from the body and you're going to secrete it across these epithelial cells and into the duct. This is kind of a generic picture, and it will differ slightly per gland, but all of them will have the same process of taking things like sodium and chloride, which we have plenty of in our body and should not have much of in this duct because it empties to the outside world, so it's constantly emptying. The gradient is to move these across the cells, so it will move across the basilar membrane and then across the apical membrane and be in the duct. Same with the chloride. Okay. It's kind of a convoluted way of doing it, but what we're doing here is we're changing our concentration gradients. We have all this sodium and chloride here. Now we put a whole bunch of it into the duct. This immediate area is going to be lower solute now. It's going to be higher water. And you've got all this salt and less water right here. You now have a gradient to move your water. So this is the idea of water follows salt, which really just means it's moving down its gradient. So we put this salt across in order to get the water across. The thing is, we don't actually want to lose this sodium and chloride. We use sodium in every part of our body. Every unit we talk about, every organ system, you're going to hear sodium come up again. We would die if we did not have enough sodium. And so our body is designed, it has evolved in such a way that it has mechanisms to save sodium. It will reabsorb sodium any chance it gets. Nowadays, especially in the Western world, this is not such a big deal. We eat enough sodium in a day to last us several weeks. But our body doesn't know that. Our body still has these mechanisms that it hasn't outgrown, so it's still going to try to save it. And that's why eating so much salt can give you hypertension. Because your body doesn't say, oh, wow, that's enough salt, I'll start getting rid of it. It still goes, gold, I want it. And it will hoard it all. And it will drive your blood pressure up, and then you'll have serious health issues. So now we need to pull this back. But when we're in the duct cells here, we've got plenty of sodium and chloride in our body. We don't have a gradient to move it anymore. It wants to stay in the duct. That's where it's happiest. So to be able to move it, we have to do a little switcheroo. What don't I have? Green. We're going to use something else that does have a gradient to be able to power moving sodium back. So we've got these other molecules like potassium and bicarbonate. They're going to be in a higher concentration outside than in your duct, so there's no problem moving those across. And when you move them, you can transport at the same time sodium and chloride back. So now you've moved your sodium and chloride back in. And you have your bicarbonate in the duct. So what actually will exit into the outside world is going to be your potassium, your bicarbonate, and your water. Mostly water. This is particularly true for sweat. Although you may have noticed sometimes that your sweat seems very salty. I mean, I don't know about you guys, but I don't typically like taste my sweat to see how it's doing. But we notice that it's salty because we're sweating so bad that it's now getting into our eyes and it burns. It's running down our face so much that it's on our lips and we can't help. Next time we lick our lips, we taste salt. The reason that we then think it's salty is just because there's so much. Normally, we want to pull that salt back. But if we're sweating that much, we're producing this so fast that we don't have as much time to pull that sodium back. So when you produce a lot of sweat, you will have more sodium in it. Salivary glands, a little bit different. Same mechanism, but we're going to talk about salivary glands when we get to digestion. We're also going to have things like amylase as an enzyme that will help break down food. So there's always more to the story than we're telling you, but this is the general mechanism. Yes?
Why does the body want to get rid of water if we need so much water in our body to function?
Well, in terms of sweat especially, we need to use that water to do evaporative cooling. We sweat in order to bring our body temperature down. So at that point, it's worth losing that water in order to save our systems. Saliva, we're not necessarily losing that because it goes out to our mouth. It's used to moisten the food that we then are going to swallow. So we'll basically just reabsorb it again anyway. Yeah. And then again, mammillary, producing milk, super complicated. I'm not touching that one. Yeah.
So is the point of moving NA in to bring water in, and then you bring the NA back into the body, and the potassium comes in?
Exactly. The point of moving this sodium in the first place was to get the water in. And I know it seems strange, like, we had a gradient here. Why don't you just push this out in the first place? I don't know. I don't have an answer for that. I could tell you that our body sometimes does very convoluted, strange things, and it's typically because it's evolved to do something, but it's taken what it already has and it's trying to jerry-rig it to do what it wants now, and sometimes that's kind of complex. Yeah.
So will these exchanges be happening mostly through like ion channels, or do we need to worry about like all those finer details?
So are these going to be moving across ion channels? Yes. We don't really talk about the ion channels yet. We haven't gotten there. But these would be, you have to have a channel to move your sodium. You have to have a channel to move your potassium. These would actually be sodium-potassium co-transporters and bicarbonate chloride co-transporters. Yeah.
So wait, you're saying that the only reason we push the Na out is because the water needs that to get through the membrane?
So we push the sodium out here at the secretory cells in order to create a gradient for the water to follow.
Oh.
Because
When like it's like changes the concentration, which helps the water?
yes, so this changes the concentration that then drives water to cross over.
Okay.
Yeah. Yes.
So when the potassium and the bicarbonate coming in, is that pushing the sodium and chloride out and just lifting the concentration gradient down again?
I missed the last part.
So the potassium and the bicarbonate, when they're going in, they're pushing the sodium and the chloride out. Is that just because it's changing the concentration gradient of the sodium and chloride?
It's not because of the changing concentration gradient so much as it is with a co-transporter, you can use the power of one. So if you had this transporter, I'm going to draw this poorly, and you have something bind here and something bind here. This doesn't have a gradient, it doesn't do anything, but this does, so it moves. That sort of sets this whole thing into moving. It like flips, and then this ends up getting pushed that way. I can't draw it well, I can't draw anyway, but that's really hard because it literally kind of turns inside out to do that. So basically you just use the movement of one and the other one hitches a ride. Okay. Yes.
So then we have sodium inside, on all around the epithelial cells, including the inside?
So we have the sodium that's readily available to move. Yeah, we have sodium everywhere. We have sodium in extracellular space, blood, or cells. I mean, we use sodium a lot. Yeah. Okay, yes.
Just curious, what's the distance between like this gland?
Oh,
Is that like an actually open area, or is it like?
so yeah, a gland typically, if you look at it histologically, a gland typically looks more like, it has all of its secretory and its duct, and then it has a very small, you can think of your sweat glands. You can't typically see those pores very well. It's very small. I don't have numbers for it though. Yeah.
So is it like the like a sodium potassium pump that you would find in a neuron, or is it different?
So is this a sodium-potassium pump that you would find in a neuron? I believe it is the same kind of sodium-potassium ATPase here. Oops. If it is a sodium-potassium ATPase, it's actually powered, not co-transport. Not sure. Okay. Good on exocrine glands. We can move to connective tissue. All right. Connective tissue is going to be these separated cells in an extracellular matrix. So remember I said yesterday, extracellular means secreted. So the cells are actually going to be secreting proteins that then make up this matrix that the cells get embedded in. And so when we look at this, we'd have, instead of epithelium that's pretty much in contact with one another, these cells are separate. They don't touch. We don't have any junctions here. We're going to have an extracellular matrix. These proteins will be different things depending on the type of connective tissue. In this case, this is going to be collagen. Collagen gives a lot of strength. It's very strong. Okay. All of our connective tissue types will secrete some amount of collagen. How much collagen depends on the cell type and its function. And that's going to be one of the biggest differences between our connective tissues, is what this extracellular matrix is made of. How much of it's collagen, how much of it is other proteins. One of the other proteins that most connective tissues will have is elastin. He's a cute little guy. As the name and the way I drew it suggests, this is springy. You can actually, a good healthy elastin, you can kind of stretch it and let it go and it springs back. This is stuff that you'll see like in your skin, where you can pinch your skin and let it go. That plus hydration levels, but you could do it more with your face. If you pinch and let it go, it should snap back. But as you get older, this elastin doesn't do as well. Your cells are not producing as much, and you're more likely to wrinkle because your skin is not going to spring back the way it used to. So this is very elastic. There are other types of extracellular proteins, and we'll talk about each one when we talk about the specific connective tissue type. So these are all extracellular, read secreted proteins. Sorry. All right. Let's do, yeah. So these 4 different subtypes of connective tissues all come from the same type of stem cell. They're all going to be coming from a mesenchymal cell. So like most stem cells, mesenchymal cell can become anything that it's within the connective tissue. So this is not a pluripotent stem cell. It's a connective tissue stem cell. But one mesenchymal cell can become either cartilage, connective tissue proper, bone, or blood. Of course, once it makes its way down one of those pathways, it's stuck on that pathway. It can't go back. So we're going to talk about the specific cell types that we have in each of those different connective tissue types. And then we'll talk about what that makes up, and eventually talk about the type of proteins in that extracellular matrix. So if you start with these mesenchymal stem cells, this could become a cell called a chondrocyte. And chondrocytes are the cells that will make up cartilage. We've got 3 subtypes of this cartilage. One is going to be fibrous cartilage. 2 is elastic cartilage. And 3 is something called hyaline cartilage. And we'll look at each one of those cartilages and the breakdown of proteins for them. Okay, this mesenchymal stem cell also could become a fibrocyte. And a fibrocyte is the cell for connective tissue proper. This is going to be things like your dermis, or things like ligaments and tendons. If this mesenchymal stem cell were to become an osteocyte, this would lead to bone. And then finally, if this were to become a hematopoietic stem cell, this would lead to the formation of blood. Anytime you see hemato, you should think blood. This brings me to a point I wanted to make for you guys too, though. For your exam, you're going to have those 3 fill-in-the-blank questions where you actually have to write in words. You do not have to spell them correctly. As long as we understand what you're trying to say, you'll get points for it. So just try to do it phonetically. Okay. All right. Questions about the breakdowns? Well, let's look at our cartilage first then. Okay, so we said that this is generically speaking what connective tissue looks like. It will all have these cells and an extracellular matrix. But if now we label this as cartilage, then we know that these cells are chondrocytes. All of the cells in this cartilage will be chondrocytes. Okay, so anytime you're talking about a connective tissue, all of the cells will be the same type. But the extracellular matrix will vary depending on the type of cartilage. So we said of our cartilage we had Cartilage. Fibrous. Fibrous cartilage is very tough. All right, this is the stuff you're going to find in things like the meniscus of the knee. So you've got these two bones that are on top of one another. And every time you stand, you're putting your full weight on that. So we need some kind of padding in between there. And we use this meniscus, which is a fibrous cartilage. The other place you'll often see this is going to be the intervertebral discs. So again, you've got bones running all the way down your back, these vertebrae, and in between them you have pads because those bones are going to be right on top of one another. So those intervertebral discs are also fibrous. In order to get that extra strength, these are going to have higher concentrations of collagen. Okay, it's still going to have elastin. It's just going to have a higher concentration of that collagen than the elastin. Our second one is the elastic cartilage. It's things like your ears, things that you know are actually cartilage, but you can move them around and they just spring right back. Ears, the bottom of your nose. So this is going to be higher concentrations of elastin. Your last one is something called hyaline. This lines articular surfaces. So an articulation is a joint. It's where two bones are coming together and we can make a movement. So again, we've got bones that are going to be right up against one another. We need to protect them. You don't want bone on bone. Anyone's ever had cartilage damage, you know how painful bone on bone is. So we have cartilage that lines the ends of our bones that are going to be in contact with another bone. You can see this, hopefully not on yourself, but if you ever eat chicken, you could take your wings apart and you could see the ends of the bone. You'll see that there's a shinier and slightly thickened portion at the ends. That's hyaline cartilage. I hear a lot of people say that this is like a bluish tint. I've never seen that, but if that works. Bluish tint. These are going to have collagen and elastin, but they're going to have something extra. They're going to have glycoso, amino, glycan. Just kidding, that's it. Glycosaminoglycans. It's long enough as is. The name tells you that this is sugar peptides. So this is just highly glycosylated proteins. They have lots of sugars on them. By the way, I'm going to put you out of your misery after you've already written this down. You can call these gags. We make all kinds of different gags. This is not one protein, it's a series. One of these is actually hyaluronic acid. You may have heard of that. Okay. And this is what is going to be predominant in hyaline cartilage. All right. I'm early. I feel like I forgot something, or you guys just weren't asking enough questions. There we go. Thank you.
So for the hyaline cartilage, would the gags be the highest concentration compared to collagen and elastin?
So the question is, in hyaline, would the gags actually be the highest concentration? That's a great question. and that's my way of saying I'm not sure. It's still going to have collagen and elastin. I don't know what the actual concentration levels of GAGs versus collagen and elastin are. Yeah.
Do the mice, I don't know what's that, the muscle stem cells, do those become mesopoietic stem cells, or are those a separate thing?
So do the mesenchymal stem cells actually become hematopoietic stem cells? Yes.
Cool, thank you.
Does a lack of elastin cause disease like osteoporosis?
Does lack of elastin cause osteoporosis? I am not aware of elastin having any effect on osteoporosis. We will talk about osteoporosis with bones, and we'll talk about why sometimes you can end up with that.
Yeah, just curious because it's springy.
True. For osteoporosis, it's typically that you're pulling out more calcium from your bone than you're putting back. That's often a dietary issue or an age issue. Yeah.
So when you're talking about the fibrous cartilage, could that also be like your sternum, like what connects your ribs?
So,
Not putting like pressure like on your meniscus or your vertebra, but
right. Fibrous cartilage, is that your, like your costal cartilages or the actual joint between your cartilages? Which one were you asking about?
oh, I thought never mind. Like is I don't know how to word it per se.
That's okay. Katie, this is your question, Miss Anatomy Guru.
What was the question?
Costal cartilages and the joint between them. What type of cartilage? Is that fibrous?
Yeah.
Good job. All right. Let's leave it there. I don't want to run into the next one yet, so I'll see you guys tomorrow.